Today we're going to take a look at section 3.5, today and Monday. We're going to look at multiplication and division algorithms and then mental estimation. So this is very much like what we did in section 3.4 with addition and subtraction. We're kind of going to start in a place where it may feel a little bit odd, but this is where your book places the material and it fits, just not with the description all that super well. We're going to start by talking about exponents. So to start with, if you have a number multiplied together a bunch of times, like we did with geometric sequences, right? This is an exponent a to the n power. The base is the a, that's what it's called, is the base, and the number that's the n is called the exponent. And it's not written in here because notationally I couldn't get it to happen, but there are n of these right here. So where I always like to start when I teach this material is establishing what the properties of exponents are and then showing you where they come from. I'm not going to ask you to repeat this back to me. I'm not going to say on a test, show me why this property holds. It's not what I'm going to do. But I feel like it's a good idea for you to have seen how it works so that if a child asks you at some point, but why, you aren't left sort of glaring at them and going, I don't know. At the very least, you can say, I'll get back with you on that tomorrow, and you'll have a place that you can go and find out, okay? So that's where we're going to look at to start with. So the first property of exponents is when you have the same base multiplied. So I have a to the m times a to the n. And do you guys remember from back in the day somewhere how these combine in a simpler way? You add the exponents. That's exactly right. So a to the m plus n. So if it's multiplication and you end up adding the exponents, what do you suppose happens when it's division? You do. You subtract the exponents. How is 3 different than 1? There's only one base on number 3. Do you see that? On number 1, we had a to the m, a to the n. But this one is a to the m, and then that is to the power n. Any idea how that's going to change things? You are going to multiply the exponents. I'm going to show you the why of all these in a minute. You're going to multiply the exponents. And then the last one that we're going to talk about, at least in this class, in proportional and statistical reasoning, if you've taken that class, we go a lot further down the path of exponents. But this one is ab to the power of m. What's that rewritten as? A to the m, b to the m, and sometimes people use the word distribute, which isn't really technically right, but I understand why people think of it that way. We're sort of moving the power n to apply to each of the a and the b. All right, you ready to see some of the justification for the y? Okay, so the first one that we're going to do is the a to the m times a to the n, which we said should be, if we are right, a to the m plus n. And in some of these, in fact, in most of these, maybe all of them today, I'm going to show you an example. Because again, if you were working with a child on this or trying to justify it, an example is a pretty good place to start with a justification for y. So let's say that we had a cubed times a squared. Okay, the structure is the same as the original generic problem, right? So a cubed means a times a times a. There's 3 of them. And a squared means a times a. Obviously, there's 2 of them. How many a's do you have? There are 5. So this is a to the power 5. And how do you get from 3 and 2 to 5? What operation does that? Addition. Okay? And you could repeat another example. If one example is not enough, just change the 3 and the 2 to something else, 5 and 4. Be more writing, but you could do that. And you'd still end up with the same result, the addition of the 2 exponents. So let's do one with division. So this is supposed to be subtraction of exponents, if we're right. So we're going to do a to the 4th over a to the 1st. So a to the 4th, of course, means that I have 4 a's. And a to the first means I have 1a. And then what? Yeah, so we do something that we sometimes affectionately call it canceling. We need to be careful with that word because sometimes things cancel and become 1, and sometimes they cancel and become 0. So they divide out is a little bit more descriptive in this case. I'm dividing each of the numerator and the denominator by a. And when I do that, I end up having 3 a's on top, which is a cubed. So how do I get from 4 and 1 to 3? It's subtraction. That's why that process works. All right, this one is supposed to be a multiplication of exponents. So let's use that same 3 and 2 that I had before. So let's do a cubed squared. So we already know, because we did it before, that a cubed is a times a times a. And squaring something means multiplying it by itself. So this is a times a times a times a times a times a, which suspiciously looks like how many a's? 6. And how would I justify that I had a 2 and a 3 and I got a 6? I multiplied, right? Yeah. And then the last one, where we said that we are going to carry the m through the problem to apply to the a and the b separately. Let us say that we had ab quantity cubed. So, if we have ab quantity cubed, then it means that I have ab times ab times ab. And one of the properties we looked at in section 3.3 related to multiplication is that we have the ability to change the orders of things, that's commutative, and to regroup parentheses, that's associative. So if we change the order and we regroup enough times, eventually we can have all the a's grouped together and all the b's grouped together to recognize that this is a cubed, b cubed, right? And we're relying very heavily upon the fact that we understand commutative and the associative property to make that happen. Okay, so now that we've talked about the why behind the rules, the properties, we're simply going to do the problems using the properties. I don't need to see anything a cubed written out, a. That's not the point of why I just did that at all, okay? We're going to use those properties inside of particular problems now. So here's our first one. We have 5 to the 10th, 5 squared, and 5 to the 4th. So which of those 4 properties will we be able to use to combine these? Addition, the first property. So this would be 5 to what power? 16, because if I add 10 plus 2 plus 4, I get 16. Okay? Literally all you have to do. Okay, one more. What about B looks different than, say, A? There are different bases, and that's really, really important. All of those rules that I gave you, or properties that I just gave you, all hinged upon having the same base when we were combining things, and this flat out just doesn't. So there are 2 different ways to do this problem, and so I'll show you them independently. The first way to do it is to recognize that this 6 is 2 times 3. Okay? Well, actually, both of the ways actually hinge upon that. But I can take the 6 and I can write it as 2 times 3 like this. And then I can use the 4th property to take that power of 4 and apply it to each of the 2 and the 3. So 2 to the 4th, 3 to the 4th. Now I recognize that not all of my bases are the same, but I do have replicated bases here, right? Like I have a base 2 twice. 2 to the 4th and 2 to the 3rd. So can I combine those? Sure. That would be 2 to the what? 7th. And then the other ones are 3s. So I have 3 to the 4th and 3 cubed. I can also combine those to give me 3 to the 7th. So this is one version of an appropriate answer in this particular problem. An alternate approach, instead of taking the 6 and breaking it down, would be to leave the 6 as it is. And instead recognize that this piece right here both have a power of 3, which means I could pull the power of 3 out and use property number 4 in reverse. They both have a power of 3, so let's just pull that out. Because 2 times 3 is 6. And now I have 6 to the 4th and 6 cubed, which is 6 to the 7th. There are desirable features about each one of these answers. The first way that we did it is nice in the fact that it's primes. 2 and 3 are prime numbers. So it's sort of broken down into its smallest pieces. The second one is nice because it's a single base as opposed to having multiple bases. Neither one's right, well, they're both right. I should say neither one's wrong. Okay, they're both correct answers to the problem. Whichever way you see it and want to do it is fine. Okay? Savannah.
In the first one, since they both have the same exponent, can you still multiply the 2 and the 3 to get 6 to the 7th as your final answer?
You could. I mean, like, it would be equivalent to now recognize that, oh, look, I can pull the 7 out and I have 2 times 3, so that's 6. So, yes, you could still get there.
If that were to be on the test, would that be considered a complete answer?
No, they're both fine as they are. Both of them are complete answers, just from a different perspective. Yeah. Any other questions? All right. I'm trying to figure out how long our lesson is and where I want to stop today. Okay. Not that I was encouraging stopping now. That was definitely not an option on the table. Didn't mean to get your hopes up. Okay, we're going to talk about multiplication strategies for multiple digit kind of things. So we did sort of multiplication with exponents. That's what we were just doing. But we're going to do multiplication with just numerical values next. So there are several methods for multiplication, and the chances are you might not have seen all of these. Okay, and there's some of them that are more efficient. There's some of them that are more intuitive. There's all sorts of cool stuff with them. So the first one that I'm going to show you, I'm not even going to show you standard algorithm on this one because you know the standard algorithm, but I'm going to start with the expanded algorithm. So the expanded standard algorithm, what it does is it takes the numbers that were given, 2 digits or 3 digits, whatever, and it separates them into their place values. So this is 40 plus 8. This is 30 plus 2. Okay, so that's expanding it. We did this expanding idea when we did addition and subtraction. Okay, so this is just the expanding idea. So when you're looking at the expanded algorithm and you're looking at multiplication, you're thinking of the numbers being multiplied in this sort of a picture. And what you do is you multiply each value out. So I've got 2 times 8, that would be 16, right? I have 2 times 40, that would be what? 80. We can do, let me change colors, 30 times 8. What would 30 times 8 be? 240. And we can do 40 times 30, which would be 1,200. And literally, it doesn't matter what order we go in or anything. I end up with 4 pieces because I've done 4 separate multiplications, right? Because there was two-digit numbers that I started with. And the result that I will get will be what I do when I add all these numbers together. So I need 1,200 plus 240 plus 80 plus 16. And we could write them out in descending order if you want. 1,200, 240, 80, 16. And we're adding them up. So this is 6, 8, 4, and 1 would be 13. Carry my 1, I've got 5, 15, 36. That's what I have written down. And at the point where you're doing the adding, you can use whatever method for adding you'd like to. So if you don't want to add standard algorithm and you wanted to add from left to right or something, you could do that. Okay, so expanded algorithm is a way of breaking the numbers down into a more intuitive type of multiplication. The thing that happens, maybe I will mention the standard algorithm because maybe you haven't seen why it feels so awkward. When you do the standard algorithm, how do you start? Multiply the 2 times the 8 and you get a 16. You write down the 6 and you carry the 1. And so that kind of feels a little bit like what we do when we do addition. That's all right. And then I have 2 times 4. So now I'm going to multiply this diagonal for no apparent reason because that doesn't happen with addition. So this feels weird already because I'm going sort of off center. I'm not going straight down and up. But so I'm going to do 4 times 2 and I get 8. And then smack dab in the middle of a multiplication problem, I'm going to add. You've got to be kidding me, right? To stop multiplication, which is what I'm trying to do, and I'm going to add. So I'm going to get a 9. And then a mysterious 0 shows up out of nowhere. We can talk about where it's really coming from, but you ask a child where it's coming from, and you're likely to get, I don't know, just write it down there. Right? And then we're going to do sort of the same thing where we're comparing across the different diagonal, right? So now I'm going to go from 3 to 8, and I'm going to get 24, and I'm going to write down a 4, and all of a sudden now this 1, it doesn't apply anymore. I'm just got to sort of like disappear it, and I'm going to write a 2 instead. And now I'm going to do the last multiplication step, which is 3 times 4, which gives me 12, and again, add in the middle of my multiplication to give me a 14, and I'm going to add one more time at the end to give me 1546 or 36. There's nothing intuitive about the way we do it. It is super efficient. Super efficient. We can do it very quickly, much quicker than what I just did on the other problem, but it is absolutely confusing. It really is. The expanded algorithm that I just showed you is nice. It breaks it down. A little more structured of a way to break it down is called partial products, and this is probably my favorite. I really, really like partial products. It breaks it down into the numbers 40 and 8 and everything just like the other one did, but it does it in a graphic way. So 8, 40 and 8, 30 and 2, and what we do is we're going to make a box. Okay, so draw a box for me. Because I have a 2 by 2, 2-digit numbers, I need my box to be split in half and in half again. Okay, if I had 3 by 3, I'd have a 9 square kind of box. 3 by 2, I would have 3 across and 2 down or something like that. We're going to put our numbers on the top, 40 plus 8, and on the side, 30 plus 2. And I'm actually going to draw you a really nice picture here in a moment of visually why this is working. We're just going to sort of jot in the numbers here. What this box does is it allows me to multiply a row and a column together. Okay, so like I'm going to multiply 40 times 30, and I'm going to write it in the box where they're on at that row and that column. So what is 40 times 30? It's 1,200, right? I can do the boxes in any order I'd like. I can start with the 8 now and do the 30 if I want. That's 240. I can do the 40 and the 2. That's 80. And I can do the 8 and the 2. That's 16. The nice thing about this method and the expanded method that I showed you first is that it isolates the multiplication. I did all the multiplication. I didn't start adding in the middle of multiplying. I did all my multiplication, and then in the end, I do all the addition. So again, at this point, I've got the 1,200, the 240, the 80, and the 16, and I add them to 1536. Multiplication first, addition last. But I'd like to show you where it comes from in terms of why these numbers were going to actually work. And to do that, I'm going to draw a much larger picture. So here is my grid. And I'm going to try to give a little bit of size dimension to what's going on. I'm supposed to have the length of this rectangle 48. That's one of my numbers. So if I were to break it apart, this seems fairly reasonable that this has a length of 40. And this has a length of 8. Okay. And the other one is 32. So this would have a length of 30, and this would have a length of 2. End up with a bunch of rectangles, right? And I find the area of the rectangles by multiplying length times width. Area formulas are done very early, and they're done about the same time as multiplication is learned for children. So these coincide really nicely. The other thing about this is that, especially if you're working on grid paper, which you certainly could when you're explaining this, if I put a grid underneath this, you could actually see all the boxes and you could count them up. I don't want to count up 1,200 boxes, so my numbers being smaller would be a little bit more helpful. Why not, right? Yeah, would be a little more helpful, but you get the idea. So that the area in this box being 1,200 visually makes sense compared to the area in this box being 16. Are you with me? So that's really what's behind partial products, is it's this way of visually describing the area of some rectangles. And then the total area is the sum of all the rectangles. This is my favorite one. My 13-year-old daughter, school comes easy for her. She just doesn't have to work real hard. And she works really hard anyway because that's her nature as well, but she just gets things easily. And so when she hit like multiple digit multiplication, this kind of multiplication, and didn't come easily to her, she got very frustrated. I'm sure you will have kids at some point who hit those points, and maybe you have been in those positions too, where you're like, it was always easy before, and all of a sudden now I'm just not getting it. I showed her partial products. She didn't like that one. She'd learned the standard algorithm at school. She didn't understand it. She was making mistakes. It wasn't working for her. But this is the other method that I showed her, and it's called the lattice algorithm. And for her, this really made sense. And you will be encouraged to know she doesn't do lattice algorithm now. She's totally fine with the standard algorithm. It was sort of an intermediate step for her, but it allowed her to get to the point where she could move into those more efficient ways to do it without just, bombing all of it until she got there. So let me show you lattice. I've mentioned the lattice algorithm for addition already, and it's very similar. So we're going to create a rectangle like we did before, a 2x2 rectangle because I have 2-digit numbers. The difference in this method is that it is place value specific, but I don't write down 40 and 8. I just write down a 4 and an 8. And I don't write down 30 and 2. I just write down a 3 and a 2. Okay, so I just use the single digit in the place values. And what I do is I split my boxes like I did with addition, like this. Okay. So again, like the partial products, I'm going to use the row and the column that something's on, and I'm going to multiply. So it's 4 times 3. You can do any of the boxes in any order, but 4 times 3 is 12. So the 10 digit goes in the top corner, the 1 digits go in the bottom corner. 8 times 3 is 24, so 24. 4 times 2 is 8, so it's a single digit number, just goes in the bottom corner. 8 times 2 is 16, so this is 1 and 6. Okay, everybody good? Nice. Now, again, like what we were doing when we did addition, we're going to add along diagonals when we're done. So again, this just does a really nice job of isolating the multiplication compared to the addition. And it gives a really cool graphic, like a visual for what's going on. So I'm going to extend my diagonals down. And if you want to, you can draw this out here, whatever. So you do have to start in the bottom right-hand corner for this to work. So this will be a 6. And then sort of moving one diagonal to the left, I have 8 plus 1 plus 4, which is what? 13. So I write down the 3 and I carry a 1. I have 1, 2, and 2, which is 5. And then the last diagonal is a 1. So my result is 1536. So you just don't know what's going to work for what kid, and having multiple approaches is always a good idea. I think I have time to show you both division algorithms, and then we'll be out of time and in a great place to stop. All right, 2 division algorithms, all we're going to do. One that you know, standard algorithm, and one that's called repeated subtraction. My son, this is what's wonderful about having kids at the age that you guys are going to teach. My son comes home with repeated subtraction the other day, and my husband says to me, I've never seen this before in my life. What in the world is he doing? And I'm like, well, there's really a good reason behind it. And he's like, yeah, I don't think so. So I tried to explain it to him. I still haven't gotten buy-in, but you know, we'll work on that. So the standard algorithm hinges on the fact that you know your multiplication tables. Agreed? It really does. So for kids with learning disabilities, for memorization problems, this is a really difficult thing to do. Because every single time that you're trying to learn, you're trying to do a division step, you have to go back to figure out what the multiplication fact is that you're missing. So that's one sort of inherent problem with it. The other thing that's inherently problematic with it is that it works okay for dividing by single-digit numbers because you know multiplication tables for fives, you know, in a traditional sense, typically speaking. But if you're dividing by 23, you don't know multiplication tables for 23. And so it's really difficult to divide by 23, right? Because you didn't memorize that. And so there's some guessing along the way, and sometimes you make mistakes and have to change things. So let's do it for 5 for the moment here. And you usually ask yourself something like this. How many times does 5 go into 6? And your answer would be 1, and you'd write it above. 1 times 5 is 5. You write it down and you subtract. 6 minus 5 would be 1, and you'd carry the 2 down to give you 12. How many times does 5 go into 12? 2. 2 times 5 would be 10 and subtract, giving me a 2, and I bring my 3 down. How many times will 5 go into 23? 4. 4 times 5 would be 20. I subtract, and I get 3. So my answer is 124, and at this level, kids usually write remainder 3. As you get older, we start working with fractions, but not at the level we're talking about, okay? 124, remainder 3. Okay, super hinging upon those multiplication tables. So I'm going to show you repeated subtraction for this, and you can see what it looks like. Now, it is not repeatedly subtracting 5, because that would take forever. But what we do is we subtract a 5 in the column where I can still do so. So I can subtract 5 minus 6, and I put zeros here, right? So I'm really not subtracting 5, but I'm subtracting 5 times 100. And it's always times powers of 10. Okay, so I'm not going to subtract 5 times 20. That's not what is ever going to happen. It's going to be 5 times 100, 5 times 10, 5 times 1,000, 5 times 1,000,000. It's always going to be a power of 10. So I can do this. What is 623 minus 500? 123. Now I can no longer subtract 500. Agreed? I can't. So I can't write down 500 again, but I can write down what? 50. Because 50 would be 5 times 10. 123 minus 50 is 73. Can I subtract 50 again? Yes, I can. 50 times 10, and I would get a 23. Okay, now notice what I'm doing. Somewhere over here, you've got to keep track of what you have been multiplying the 5 by. Does it have to say 5 times 10? No, you could just write times 10. That'd be okay. We're going to need that piece of information when we're done. Our answer is going to come from there. 23, can I subtract 50 again? Nope. So what am I going to subtract? We're never going to multiply by anything that's not a power of 10. It's just going to be 5. Just 5. Because 5 times 1, and 1 is a power of 10. It's 10 to the 0. Okay? So the part here at the end becomes a little tedious because I have to keep subtracting 5s. This is the part where my husband was like, no, thank you. Are you getting to that point? Okay. Fair enough. So I did 5 times 1 here. Oh, did I write something down wrong? I moved too fast. Thank you. 18 and 13. There we go. Then we've got another 8. And eventually I get to the point where I cannot subtract another 5 and I'm stopped. This number at the end is the remainder. The answer is how many times I multiplied 5. So there's 100, 20, and then 4. 124, remainder 3. This is not efficient. Okay? Definitely not efficient. However, I didn't need to multiply 5 by anything. All I needed to know is 5 times 1 is 5. 5 times 2 is 5, 0. Or 10 is 5, 0. 5 times 100 is 5, 0, 0. That's really helpful. It's really helpful. And it's especially helpful if it's a multiplication table that you don't know, like times 23s, right? Because all I got to do is subtract 23 or 230 or 2,300 every time. And there's where the benefit lies.